become such a part and parcel of our lives. We, with the extensive and robust and ruthless ways in which we put mathematics into use in our daily lives, we've almost forgotten how to appreciate this as something fun. So I would request you all to sit back for next 20-25 minutes and let's appreciate mathematics as something fun on LabVIEW. So let me introduce you to the mathematics palette, which you should be finding on your block diagrams. Now, on this palette, you see a lot of functions like the numeric function, the elementary function, integration, differentiation, polynomial functions, and etc. So let's just take a look closer into these functions and let me tell you about some use cases of them in general. And then we're going to switch to LabVIEW and see how to put them into work. All right, so the numeric palette, which most of you would already be well versed with, is used for some simple and compound arithmetic operations, as you can see. It can also be used for some complex number functions like extracting the real and imaginary part or out of a complex number, or it can be used for some conversions, some basic conversions from different representations of data, or it can be used for some scaling operations. The elementary and the special functions, so these elementary and special functions can be ranging from trigonometric functions to hyperbolic functions, exponential functions. You know what? You could even attempt solving a Schrodinger equation through the Bessel, Kelvin, and Gauss functions available. Or it could be some simple discrete mathematical operations like binomial coefficients, the GCD, LCM calculation, linear algebra, of course. So you have the matrix operations that you can perform. It could be a determinant, it could be an inverse, taking a transpose, doing multiplications, taking a conjugate, or doing some submatrix operations, and etc. Some curve fitting algorithms. Now, some of the basic and the most commonly used curve fitting algorithms like a linear fit or a spline fit or a non-linear fit and logarithmic fit is of course there, but you could also have your own custom designed algorithm which, taking reference from one of these existing algorithms, you can make on your own. Probability and statistics, some basic operations like a mean, median, variance, or taking correlation whether cross or auto, and for display purpose you also have a histogram. Interpolation and extrapolation, it could be again linear, spline, Hermite, which are the most commonly used algorithms. And like I said before, you could design your own interpolation polynomial, and that would make that would be your own custom interpolation and extrapolation algorithm with greater accuracy. Some simple basic integration and differentiation. We could do nothing without it, isn't it? Now some polynomial equations like arithmetic and polynomial operations, taking an integral or derivative, and some commonly used polynomials like the Bessel, Chebyshev, and the Legendre polynomial. But you know what? Maths is best learned by writing equations. Now, unless you don't see these equations in the written format, pictures don't really make much sense to you, doesn't it? So, what I have for you is the script and the formula palette. Now, the script and the formula palette is nothing but a way for you to write down statements. You know what? Not only write down statements, you could extract these statements from a LaTeX file. You could extract these statements from an equation written on Wikipedia with all those Greek symbols and notations. You could extract all of them, put them in the script and formula, and trust me, LabVIEW understands them. We'll see how. So what do you say? Let's do some LabVIEW. Now, I have a new BI wherein I'm going to start off with probability and statistics, and I'm going to show you how to plot a histogram. Too simple. So this is the mathematics palette. Let's spin it up. Now, before plotting histogram, I need data, right? So let's just simulate some signal. I take an express VI because I want to save time over here. I choose a DC signal and I want to add some noise onto it, so I'm going to add some Gaussian white noise onto it. I'm going to increase the standard deviation over here, and just look at the preview. You see the signal varying from 3, -3, at times it even goes to 4. Just keep a reference of this. Alright, we have our signal ready. Now what we're going to do is we want to plot a histogram, and how difficult can it be? It's just an express VI. Now let me increase the number of bins because it's a very randomly varying signal. I'll set the maximum value to 4 because we saw it at times went to 4. Look at the preview. This is how it should look like when the input signal is as what is given above. Alright, good enough. Now that we've used the palette, let's close it up and let's make the connections. Great. So we have the connections ready. Let's create the histogram. All right. Of course, we need a while loop because I need to see the continuous data. So, all right. And why not view the actual signal as well? So let's have another graph over here. We have the signal wired up. Great. So let's now focus our attention on the front panel. You have the signal graph, which will show you the actual DC signal with Gaussian noise, excuse me. And then you have the histogram, which will show you the histogram. So let's get the code running. And here it is. Let me just quickly add some delay so that we can view better. Yeah, 1 will be too much, so let's add 0.2 seconds over here. All right. Great. So you see this, and this is the histogram in front of you. Now, whatever analysis you want to perform over the histogram or the data that you're getting over the histogram is up to your own discretion. So you can go ahead from here and do whatever analysis in probability and statistics that you want to. And you all saw how easy it was. All right, let's see what else we have. Now, after this, let's try out something with the matrix. All right, so let me just quickly drop in a real matrix over here and put some values, whatever comes to my mind. All right, now what would you want to do? Let's perhaps take an inverse. Again, I go to the mathematics palette and I go to linear algebra, and here is the inverse matrix, and put it up over here. Make a simple connection. Matrix type. This is a general matrix. Now let's just look. You could have, depending on what kind of matrix you have, you could have a diagonal matrix or a lower triangular, upper triangular. This is a general one, so we'll take the general matrix and we're going to make an indicator over here. All right, let's just make things look more arranged over here on the code. Okay, so do we know if it's right or wrong? So we all must have read the simple rule when we first introduced to matrix, that the simple way to calculate the inverse of a simple general matrix 2 cross 2 would be to swipe 4 with 1 and 1 with 4 and interchange the sign of 2 and 3. So let me just make 3 a negative number so that we can see it better. Alright, so a simple way to calculate the inverse would be, I'll put 4 in place of 1, 1 in place of 4, that is make an interchange over this diagonal, and over this diagonal multiply the two elements with minus. So interchange the signs on this side. Alright, so this is not enough. You also need to divide by the determinant. So let's see if you have a way to get the determinant and confirm if what we've done is correct or not. So I have the determinant BI and it needs the input matrix. Okay, let's see what the determinant is. All right. Okay, so if 4 was here, then 4 divided by the determinant would mean 0.4, correct? Now 1 would be in 4's place and 1 divided by 10 would be 0.1, correct? Now 2 now will become minus 2 because the sign is to be interchanged, and minus 2 divided by 10 would be 0.2, correct? And 3 would be 3 because it would take the sign of 2, and 3 divided by 10 would be 0.3. Perfect. So this works. Not only this, you could do a lot more operations on the matrix. Now after matrix, what we're going to see, let's say we do curve fitting. Let me demonstrate a linear curve fitting for you. And in this case, I'll first run the demo and then I'm going to show you how I made it. All right, so let's have a good number over here. The number of points that I'm going to be using for curve fitting, so like a curve fitting algorithm. Okay, let me just quickly tell you what curve fitting would actually be doing. So we'll have a set of data. Now these set of points will actually belong to a particular curve which we wouldn't know, wouldn't have much information about. Now that's what we're supposed to do, right? That's what a curve fitting algorithm is supposed to do. Take a set of points and assign it to a curve with greater accuracy. Now linear curve fitting would be one of the most basic things to do, not applicable in all cases in practical situations, but yes, for demonstration ability is the simplest to demonstrate and understand. So I have like 50 points, and these 50 points actually belong to a line which has an intercept of 1, which has a slope of 1 and an intercept of 0. Let's give some intercept over here, an intercept of 3. And onto this straight line, I'm adding some noise. Okay. So if I add some noise, then you all understand that the line wouldn't be as straight as it sounds. So that's the information about the set of points. So the set of points that I'll be having and feeding into my curve fitting algorithm will actually be belonging to a line which has a slope of 1, an intercept of 3, and over which a noise of 0.7 has been added. So let's go on to the block diagram and see how I'm doing that. So the first VI that you see is a linear data VI, which is doing nothing but taking this information of the slope, intercept, and the noise amplitude and generating the set of data points. Now when I have the set of data points, I have this simple VI which is called as linear fit VI, which you'll find in the mathematics palette. This linear fit VI will take these points and will also ask from you what is the method that you want to deploy in the curve fitting algorithm. Now the method could be a simple least square, a bi square, or least absolute residual. So for example, if I had a bi square, then I would be doing nothing but minimizing the weighted sum of the squares, while if I had the least absolute residual, then I would be minimizing the weighted, the absolute difference of the squares or of the residuals. So let's just simply see how it works over here. Let me expand it. All right. So here it is. You can see that my curve fitting algorithm is calculating an intercept which is ranging from 2.9 to 3.1, which is I mean, good level of accuracy. You decide whether good or bad. Then the slope, which is again somewhere close to 1. Now, obviously, if we decrease the noise over here, we should see the results improving. And the results will also vary when you change the algorithm, the way you are actually calculating the curve fitting. And if I take least square. So pretty much simple over here, the linear curve fitting. I will just quickly run through the block diagram again. So nothing. The first step is to get a set of data points that you actually want to fit into a curve. So how am I doing that? I'm using a linear data VI, which is taking in a particular slope and intercept on the y-axis, creating a line out of it through consisting of number of points as mentioned by you. Then you add some noise amplitude onto it. So now the points that you have will actually not lie on a straight line, right? And now your task is to assign a curve to the set of data points for which you go and give a call to linear fit algorithm, which you'll find in the mathematics palette. You give the x value, you give the y value, and then what you're supposed to be doing is give a method for the curve fitting, which could be a least square, bi-square, etc. like I said. And then the curve fitting algorithm tries its best that it can and gives you a slope and intercept. Now, this is one. You could have your own spline fitting. You could have your own curve. You could use a logarithmic fit, or you could design your own custom fit. Another thing that I'd recommend you to do is type Control H. Go to the detailed help, and what you expect to see is the algorithm which is actually implemented in getting this subview. And that's going to help you a lot if you were ever trying to make your own curve fitting algorithm. Great. So let's see something more. Let me open a new VI, and like I promised, we're going to talk about the script nodes for those who are more comfortable with statements. All right. So we have the mathematics palette again. You're going to go to script and formula node. Let's take the formula node and see what it does for us. All right. We'll try out some simple things on the formula node. Now, on this formula node, the first thing that I'm supposed to do is add some inputs. So let's add inputs. Let's name it A. Let's add another input. Name it B. Let's have another input. Name it C. Great. And we'll also need some outputs, but before that, let's decide what we want to do with these inputs. So let's say we want to make an array, as simple as that. So if I were to make an array, I would need a for loop, right? So if I need a for loop, I would need iterations for it, right? So let me just declare a variable I, which should be of the type int32. I shall be using this for changing the iterations of the for loop. Then we also need an array, right? So let's have a floating point 64-bit array of how many elements? Say 5. All right, so now that we have an array, we also know one of the outputs, so let's just quickly make an output. Should be named as array. And now let's make a for loop for I equal 0. Okay, what should the element be? Say A plus B plus I. Sounds good over here. Now we need to assign values to A and B, which were the inputs that we had declared. So let's just quickly assign some values. Not using C in the moment, so let's just do away with it. And of course, we need to create an indicator for Y. Now, LabVIEW intelligently decides that this is an array, as we have already declared it inside the node. We also expand this array because we're expecting to see some 5 values over here. All right. Great. So what we have here is an output array. First element is 1 plus 2 plus I in this case is 0, so it's 3, and then subsequently you keep on adding 1, which is due to addition of a 1 in the I, so it's 3, 4, 5, 6, 7. Sounds good, this was simple. Let's also try something more, which should be adding an input. This time let me have an array. All right. I'm planning to make a sine waveform. So let me take some values: 0, 30 degrees, 60 degrees, 90, 120, 150, 180. And this is 7 elements. So if we want to create a sine wave out of these 7 elements, let me declare another array with 7 elements. Let's take this array and wire it into one of the inputs, which is C. Great. Now we want to get the sine values into Z array. For that, a good old friend for loop. I can use the same I, right? So I is equal to 6. Okay. This time it's Z I equals sine X I, which would mean it would be sine of the corresponding element in the x-axis. It's X or C? It's C, right? Or let's just name it X over here. All right. Okay. So how do we view this? We need to, of course, add another output, right? And what will be the output named? Z, because that's how we declared it. Now let's quickly create an indicator for it. This will be the sine values. This will be the output array. Okay. Looks like we're done. Let's also view the values to see if it works for us. All right, let's go ahead. Okay, so we seem to have gotten some values over here, but is sine of 30 degrees 0.98? There seems to be some issue over here. So it looks like the sine function will take the rad values. So it's considering 30 not as degrees but as radians. So let me introduce you to something called as an expression node, through which I'm going to do the conversion of degrees into radians. And you're going to find it in the numeric palette over here. This is the expression node. Now if I were to convert degree to rad, then I would write it as parentheses open x divided by 180 multiplied by pi. Sounds simple? So instead of putting this array directly into x, let's make it go through this converter. All right. Here it is. This sounds familiar. Sine of 30 is 1 by 2. So here is the formula node for you and the expression node for you. So there's enough. This was just a glimpse of what is possible with the maths toolkit, maths palette. But there is a lot more that you can do with the maths palette, and I'd highly recommend you to play along with it. And just like I said, we sort of have extensively and ruthlessly used mathematics in our daily life and daily uses. And in that way, we've forgotten how to appreciate the fun part of it. Now, LabVIEW is one platform where I can do maths for fun. And going back to the slides, I am really glad announcing the winner of the last week's contest, who is Mr. Prashant Patel. Heartiest congratulations, sir. You will receive a personal message in your NI community profile inbox for further details. And let me tell you that you were facing very tough competition from people across the country and across the world. And I appreciate everybody's efforts and highly encourage you to keep participating in the contest. Now, before giving you this week's contest, we have something really enticing for you, and for that I'd like to invite Jagriti to come on air and share the same. So handing it over to Jagriti.
Thank you so much, Shivansh. A very good evening to all of you. So I'm here to announce a very interesting competition that we have come up for the month of August. So what we plan to do is we plan to integrate Webcast Wednesday with NI Days. So let me talk a little on NI Days. So NI Days is this annual conference we hold to bring together engineers and scientists from India, Russia and Arabia, representing various industries to discuss and showcase new technology for software-defined systems. And this NI Days, we're going to have a very special guest with us, Dr. James Trishard, CEO and co-founder of National Instruments. So how can you be a part of this? So we're going to be giving you a chance to be there at NI Days and meet Dr. James Trishard. And how we're going to be doing this is for the following month of August, we're going to have contests just like we've been having in the past. But the only difference is from now on, every contest will be awarded points. Points based on the functionality of your code, based on the aesthetics, based on the programming practices that you've used, will be awarding you points. And the top 5 who have most actively participated will get a chance to represent Webcast Wednesday Zone in the exhibition floor during NI Days 2013. So you'll be right there being the face of Webcast Wednesday and talking to customers about how and what Webcast Wednesday is all about. Also at the end of this, one winner from those top 5 will be getting a personal certificate signed by Dr. James Trishard. And also these awards and these points will be put up on the community in the form of a scoreboard, and you can view these week after week. So now coming to the contest of this week. Okay, so this week we want you to create a calculator in LabVIEW based on the operations that Shivan spoke about today. So for example, you could include some basic arithmetic operations, compound arithmetic, some trigonometric operations, matrix operations, and polynomial equation solving. So we will be, like I said, awarding these based on a couple of criteria like functionality, aesthetics, and programming practices. Now you could use the state machine and the event structures in order to achieve your results. So the link to the question on the community will be posted right now on your chat windows, and you can click on that and go directly to the question and try getting the answer right to this. You can also ask us your questions on the community, and we are here to help you get your results. So the LabVIEW enabled community is a platform for you to have an extended discussion after every Wednesday, after your webcast every Wednesday, and the winner every week will continue to get his or her 50% discounts in CLAD, and those of you who attend 20 webcasts will get a free attempt at the CLAD exam. So this is how you can reach us. You can go to www.labviewenable.in, click on the Webcast Wednesday graphic that you see on the top left, and that will take you right to the webcast page on the community. So see you all there. Thank you so much for attending. If you have any questions, you can post them right now on the chat window.